Hey guys, welcome to our first round of video notes here. So hopefully this all makes sense and I didn't make any crazy errors on this, but we're looking at kinematic equations 2 and 3. That'll be section 1.7 that we'll be looking at. So the first thing we look at is what kinematic equation 1 does. And I keep asking you guys, what does it do? And not to tell me what the equation is, but it does this. It allows us to determine the velocity of an object based on its acceleration over time. Equation 2, the second one, determines the position of an object over the time based on its initial position, initial velocity, and acceleration. So off to the right here, we have our equation 2 that we'll use. You'll see it written in two different ways. The first one is d equals v naught t plus 1/2 at squared. D is basically the distance or the displacement it travels. Down there at the bottom, that xf, if I subtract xf and x naught, so xf minus x naught, it means distance or displacement. So those can be used interchangeably at times. So write down these equations, hit pause on this whenever you need to write down things, but I'm just going to walk through a couple of examples to how to use these. So the first example, an object accelerates from rest with a constant acceleration of 2 meters per second squared, so positive. How far will it have moved after 9 seconds? So here's my givens. My x naught just basically means I'm starting from some original origin, so that's why we use it like that. And then I know my initial velocity is 0, I know my acceleration, and I know my time, 2 and 9 respectively. So we're going to use kinematic equation 2. So I use that first d1. I'm going to simplify based on the given. So once again, it's good to show your work on this. So there's the equation that I'm going to use. And the v naught term goes away. Next, I'm going to substitute the givens. So there's my substitutions. 1/2, the a is 2, the t is 9. When I crunch that number, I get 81 meters. So it will have moved 81 meters after being accelerated for that long. Example 2 starts off with the same kind of thing. We have an object starting at rest, travels a certain distance in a certain amount of time with a constant acceleration, and now we're tasked with finding the acceleration. So the first thing you know is the givens. My initial position is 0, initial velocity is 0, distance and time. Again, we're using kinematics equation 2. Using that first form, d equals v naught t 1/2 at squared. Simplify based on the givens. So again, the v naught term goes away. In this case, we're solving for a. So my x equals 1/2 at squared, or d, so I substituted the value there. So that turns into this right here. So make sure we can follow the algebra to get to the blue equation there. Substitute and solve. We should get about 3.6 meters per second squared for the acceleration of this guy. Next example, an object, again at rest, accelerates for a little bit. How long will it take for that to travel 3,400 meters? So this is a long thing accelerating. Maybe it's a train or a plane or something. Here's my givens. Once again, starting from rest is 0. The initial position is 0. Then I have the distance traveled and the acceleration rate. Using kinematics equation 2, I'm using the d form again. Simplify based on the givens. So d equals v naught t 1/2 at squared. The v naught term goes away. In this case, we're solving for t. So there's my initial equation. That should turn into this guy here. Once again, make sure we understand how to follow the algebra there. There might be a little lesson that we work on. Substitute and solve to get about 14.1 seconds. So that's using equation 2, d equals v naught t plus 1/2 at squared. And then we have a third equation that we use. And so here it is. I'm not going to do all of the algebra to figure it out. But what we do is we basically plug 1 and 2 into each other for using for t, and the result is kinematics equation number 3. The x minus x naught is sometimes substituted for delta x or just d. So depending on the question we're looking for, it kind of works itself out. This equation is used when we don't know what time is. So on this one, we don't know time. So an object accelerates from rest with a constant acceleration. How fast will it be traveling after it goes 21 meters? Here are my givens. Oh, I have my little equation off to the side there. We're using equation 3, so it's v squared, v naught squared. So remember, the v squared on the left, that's the final velocity of the object. Looks like that's what we're looking for. So simplify based on the givens. The v naught term goes away, and that x naught is just starting from the original position. So I have v squared equals. So when I solve it, so I got ahead of myself there. I solve for the v, or the final velocity. And again, substitute and solve. So we should get about 17.8 meters per second. Second example, accelerating from rest to a speed over a distance. What acceleration did it experience? Here are my givens. Once again, I don't know time. I could ask a part B for time, and we have to go back and find some of the extra equations. So that's kind of what our quest assignment will look like for this. We're using equation 3. Simplify based on the givens, so the v naught term goes away and then the x naught term goes away, leaving me with v squared equals square root 2ax. We're solving for a, so it's under the radical. So when I solve for this, once again, make sure we understand where all of the terms go. Substitute and solve. We should get about 5 meters per second squared. Last example, so we're almost done here. We have an object that accelerates. As a result, it accelerates from rest to 24 meters per second. What distance did it travel during that acceleration? So here are my givens. Once again, we're using equation 3. So I have... here's my equation. So simplifying, I have my v naught term goes away, and then again my x naught term, leaving me with v squared equals 2ax. Solve for x. So I should get v squared over 2a. And again, substitute and solve, so I should get 42.4 meters for the distance it traveled. Once again, none of these questions asked me for time, and I didn't necessarily need it for these questions. Okay, so there's our quick video notes. So we're really just working on using these new equations. So make sure you review them, write them down so we can use them. So for classwork, make sure you complete this. Equations 2 and 3 classwork, click the link. And then for homework, for the problem set for this one, we'll be using the quest assignment that is up and published. So make sure you do that. All right, thanks for watching. I'll catch you guys later. Bye.